Okay. Okay. Let's make sure that you understand the sine and cosine, first of all. They're the two most important. Okay. So I'm going to start out with the sine. Now, there's some very important points on this. Are you into radians or degrees? Have you had radians? What are they using more frequently, radians or degrees? Okay, let's label this with radians. So that's 2 pi. What you always need to do is quarter this up. In other words, the 3 most important or the 4 most important points are where the sine is equal to 1, where it's equal to 0, where it's equal to -1, and where it's equal to 0 again. In other words, this point, this point, this point, this point, and this point. That's always what you need to know most. Now, sometimes they will alter the original function such that the period is not 2 pi. Maybe the period is 3 pi over 2. And then you have to quarter that up. So this process of quartering it up is very common. Okay? All right, let's look at cosine. Now, incidentally, before I move to cosine, this does go on. In other words, I only drew 1 period of it. Goes on forever, goes to negative infinity and positive infinity. Okay? It's where the function gets back to its starting place. In other words, it's where it starts repeating. Notice that I've drawn in red 1 complete period, and then you could draw another period, which is a duplicate of the first one. In other words, when I get back to the point where I'm going up again, that's going to be 2 periods right to there. So a period is graphically defined as where it starts over again. And it's also why the sine of 30 degrees is equal to the sine of 390 degrees. In other words, you can always take multiples of 360 out and get the same thing. In other words, coterminal angles, the trig functions are always the same. That's also equal to the sine. If I added another 360, I would have 750. Okay, if I go backwards and I subtract 360, that's also the sine of minus 300. So when we graph them, we usually just graph 1 period of them. Sometimes you'll see multiple periods and they'll ask you questions about it, but 1 period is enough to know everything you need to know about it. In other words, when you graph 1 period, you can figure out the rest. We're having a little bit of audio issues I can hear. All right, here, let me erase some of this stuff and talk about cosine. Cosine starts at 1. Still has a period of 2 pi. Notice that at this point here, if I continue it, I'm at the same point as I was right there. In other words, I'm going to go down. Okay, so that's one complete period. Now, if we quarter that up, the key points are our same key points. Pi over 2, pi, 3 pi over 2. In other words, at those values on the x-axis, the trig function reaches its maximum, minimum, or 0. Okay? This is also 1 minus 1. So, if I talk to you about domain of these functions, it's negative infinity to positive infinity. If I talk, what's the range of both of these functions? Okay. And the third one that's really worth memorizing, and the reason I say that is because the other three you can figure out if you know these three. Okay? Now, the tangent one is a little different in that it has vertical asymptotes. These happen to occur at minus pi over 2 plus pi over 2. And the function is always increasing, always rising, and always asymptotic with those asymptotes. And furthermore, you have an asymptote every pi. So the period of the tangent function is actually pi. It's not 2 pi. In other words, this is 3 pi over 2. This is 5 pi over 2. And it just repeats. In other words, I've drawn 3 periods of the tangent function, whereas I only drew 1 period of the sine function and 1 period of the cosine function. So, tell me what the tangent of pi over 2 would be. Correct. You can see that it's actually going to infinity, right? So you could actually say positive infinity as opposed to undefined. Yeah. They tend to mix up these words. Undefined, does not exist, infinity. They tend to interchange them. But at some level of math, you get to a point where there is a difference between undefined and infinity. It's very clear from this graph that as we approach pi over 2 from the left side, we're going to positive infinity. If we approach pi over 2 from the right side, we're coming up from negative infinity. So I can't actually say what the limit of tan of x is at pi over 2, because the left limit is different than the right limit. And that means it truly is undefined. Okay? That's calculus that you haven't learned yet, but that's coming. At some point, you'll get into limits and calculus, and you'll learn the difference between approaching from the left or approaching from the right. And the limit only exists if both of those are the same. But anyway, there's your 3 basic trig functions. Now, let's just talk about the other 3. Okay? I'm going to draw the other 3 in blue. And the reciprocal of sine is what? What's the reciprocal of sine? The reciprocal. Okay? That means that when the sine is equal to 1, the cosecant has to equal to 1, because the reciprocal of 1 is 1. So this point has to be shared by both, and what happens is the cosecant looks like that. It sits on the top of the sine and the bottom of the sine. And obviously when the sine is 0, the cosecant has problems, right? Because all of a sudden now I'm going to be dividing by 0. So the cosecant also has asymptotes whenever the sine is 0. The cosecant is going to have asymptotes. Now let's talk about the secant. Well, the secant is the reciprocal of cosine, so the secant is going to sit on the tops of and the bottoms of the cosine curve. Now, when I drew one period of the cosecant over here on the top left, it includes the top and the bottom one. That is one period. In other words, one period of the cosecant is 2 pi long, just like the sine. Their periods are the same. Same with cosecant. And cosecant also has the same problem in that whenever the cosine is 0, it's going to have a vertical asymptote because you can't divide by 0. And remember, this thing is the reciprocal. So you have vertical asymptotes every pi. Now, that leaves the last one as cotangents. Let me erase those asymptotes so I can get the cotangent in. And again, let me put the... Now, cotangents got the same problems that cosecant and secant had, in that whenever tangent is 0, cotangent better have a vertical asymptote, correct? Because cotangent is the reciprocal of tangent. So tangent is 0 there, and tangent is 0 at pi, and it's 0 at 2 pi. So that's pi. Hold on. That's 2 pi. And the cotangent curve is kind of the, if you took the tangent curve and reflected it over the x-axis, it would look like this, only it's shifted. But the cotangent curve is always declining like that. And notice where the cotangent is 0, that's pi over 2, that's where the tangent's going to have a vertical asymptote. So this is y equal cotangent of x. So there's your 6 graphs. Now, one of the trickiest problems they give you is they will give you a graph and they'll ask you, is that a tangent curve or is that a cotangent curve? And notice that what a negative tangent curve would look like. In a third color, I'm going to graph in green what y equal negative tangent would look like. See what's happening? That is y equal negative tangent. In other words, it is reflected over the x-axis as any negative sign of any function would be. But notice the similarity between the green line and the blue line. So if they showed you the green line and they showed you the blue line and they said which one is negative tangent, which one is cotangent, well, they both look exactly the same. The difference is this one goes from minus pi over 2 to pi over 2. This one goes from 0 to pi. Yes, this is all basic functions. We haven't even talked about the sinusoid function yet. We will, but it's pretty important to understand the basic graphs, okay? Although the sinusoid function doesn't really have the tangent and cotangent in it, but you'll still be asked questions about the tangent and cotangent. The part that they're going to spend the most time on is the sinusoid function. Have you gotten to that yet? It's called the sinusoid function. I'm going to erase my bottom half here. You have graphs of these in your book somewhere. If you don't, take a picture, pull your camera out and take a picture of that page before I erase it. You want somewhere to be able to remind you of what these graphs look like. The most important being sine, next cosine, next tangent, and then the other three. Okay? All right, okay, good. Let me erase this. And let's talk about the sinusoid function. The sinusoid function. And this can be two different ways depending on the school system. I think this is my favorite expression of it. Are you familiar with this? In this format? No, not in this exact format. An example would be, whoops, hold on. I wrote 3 and thought I'd written an S. In other words, there is a sinusoid function. Now the question is, how do you graph it? Well, do you remember pre-calc or actually algebra 2 where you were graphing transformations? All of these are transformation. That is a vertical shift. But in trig, it's called amplitude. This is a vertical stretch, right? In other words, if you go back to algebra 2, but in trig, well, this is called B, and we'll get to that in a second. B equals 2 pi over the period. But it's still just a vertical stretch. In algebra, that is a horizontal shift. But in trig, they call it phase shift. And that, in algebra, is a vertical shift. And that's what it's called in trig also, is a vertical shift. Okay? So, you can take your basic sine function and apply all of these things. In other words, if I indeed had this exact formula, well, first thing I'm going to do is shift it up 4 units, right? In other words, right now, that's at 0. Well, let's move it up to here at 4. So now it looks like this. Okay. Then I am going to apply the phase shift of pi over 2, which means I'm going to shift it to the right by pi over 2. So now it's going to look like this. With me? Now I'm going to apply the, excuse me, that is a horizontal stretch factor. Actually, it's a horizontal shrink. Okay? And shrink factor? Yeah, if you're dealing with verticals, numbers greater than 1 are stretches. I wrote this wrong. That's a vertical stretch. And this is a horizontal shrink because it's a number greater than 1. If this 2 was between 0 and 1, it would be a horizontal stretch. It's a little confusing. The vertical is opposite to the horizontal. In other words, when you're talking about vertical stretches, numbers greater than 1 are stretches, numbers between 0 and 1 are shrinks. When you're talking about horizontal stretches, numbers greater than 1 are shrinks, numbers between 0 and 1 are stretches. So this is actually a shrink. And what that means, if I draw it in a different color, is it, instead of being 2 pi in length, like your normal sine function, well, if I figure out b is 2, the period's going to be pi. So it's only going to take pi to draw this sine curve right here. You following me? What I'm doing is each one of these adjustments one at a time. The only thing left is that. That is a vertical stretch. So what that means is it's going to go up 3 times as long, come down 3 times, come back to there. So that orange curve would be basically what this would look like, this function. If they gave you that function, they said graph it, you'd end up with the orange curve. But the way you would do it is exactly the way I did it, which would be to start with what sine of x looks like, and then just make all of these adjustments. Now this is a fairly complicated one because there was 1, 2, 3, 4 transformations that I had to do. Usually you won't have to do that. In other words, let's take a simpler one. In fact, let's take them one step at a time. Okay? So, that's sine of x. 2 sine of x looks like what? What's it going to be called relative to sine of x? Yes, perfect. So it's going to go up to 2. It's going to go down to -2 and come back to there. Okay? So this would be that. Now, let's take another one. Let's take these one at a time. So that was a vertical stretch. Now let's take this. Notice the 2, instead of being out front of the sine, it's in front of the x. Since it's inside the function, it's horizontal. And it's a horizontal shrink. So if my normal sine curve looks like this, a good formula, this is called b, incidentally. And they do give you a formula that b is equal to 2 pi over the period. And you do need to memorize that, because we know what the period is, right? The normal period is 2 pi for a sine or cosine curve. So if I do some algebra on that, I get the period equals 2 pi over b. In this case, b is 2, so the period is pi. Meaning we've got to draw that curve between 0 and pi. So I'm going to quarter it. I'm going to make sure my first point is there, my next point is there, my next point is there, and my last point is there. So I'm going to draw it like this. And that's the best way to do these, is once you figure out what your period is, quarter it up. And this ends up being pi over 4, that's pi over 2, that's pi over, excuse me, what is that? That is 3 pi over 4. Halfway between pi over 2 and pi. Okay, so we covered the vertical stretch or shrink and the horizontal stretch or shrink. Okay? Let's go over the rest of them. One at a time this time. Okay, the other thing you have is vertical shift. In other words, this thing is outside the function. That means it's going to be vertical. And its up or down shift does not change the shape of the curve. So if that's 1 and this is -1, well, if I take this curve and move the whole thing up by 3 units, what I'm really doing is moving the line of symmetry up by 3 units. The current line of symmetry is right there. So I'm going to move it up to 3, draw a new line of symmetry, and draw my curve about that line of symmetry. So it goes up to 4, goes down to 2. Still goes to 2 pi. I did not change the period. Okay? Let's talk about horizontal shift. Well, I know it's horizontal because it's inside the function. Now, this is what Trig will call a phase shift. But in reality, it's just like a horizontal shift when you're graphing polynomials. So I'm going to take my sine curve and duplicate it. Horizontal shifts do not change shape. We merely move it left or right. This one needs to move to the right by pi over 2. So instead of starting here, I'm going to start right here, and I'm going to go to 5 pi over 2. Because I know the period didn't change. So the period is still 2 pi. And when I get to right there, I need to be there. When I get to there, I need to be there. I need to be there. So that's what this curve would look like. The sine curve shifted to the right. Okay, we've covered all 4 of the typical transformations. The only ones we haven't covered are the reflections. Let's talk about that. Minus sine x. What kind of transformation is this? What's the minus sign mean? It reflects it over the x-axis. And I call that a vertical reflection. which matches my system. In other words, anything outside the function is vertical, anything inside the function is horizontal. So this is a vertical reflection. So it's going to look like this. Okay? And the very last thing you can have is a horizontal reflection, where the negative sign is inside the function. And what that means is you're going to reflect about which axis? Correct. Actually, well, this might finally have shown me why they don't talk about it the same way. Because this appears to be the one exception. In other words, this is not a reflection about the y-axis. I never realized it until just now. I've never been through each of the 6 transformations before, one by one, and seen that this is not. This is a reflection about the origin. Hold on a second. It's got to be a reflection about the y-axis. It's got to be. No, it isn't. No, it absolutely is not. No, hold on a second. The one thing I know is that the sine of minus x is equal to minus sine of x. So this blue curve can't be right. Or can it? All of a sudden I'm confused about this. Hold on a second. The sine of minus pi over 2. Okay, let's label this. This is pi over 2. This is minus pi over 2. The question is the sine of minus pi over 2 1? And it is not. It is minus the sine of pi over 2, so it is minus 1. So this blue curve is not correct. It is not a direct reflection over the y-axis. Dang, you learn something new every day. This is what it is. And notice it's also an odd function as opposed to an even function. An odd function says f of minus x equals minus f of x. And if that is true, then it is symmetric about the origin. An even function says f of minus x equals f of x, and an example of that is cosine. If you look at the cosine of minus x, it's equal to the cosine of x, as opposed to the sine of minus x, which is minus sine of x. It's very interesting. I have spent 10 years trying to figure out why they treat trig functions so differently than they treat polynomials. Because it seemed to me like the 6 transformations were identical, and they should just call them that. They don't. Instead of a vertical stretch factor, they call it amplitude. Instead of a horizontal stretch factor, they call it b, which is 2 pi over the period. In other words, they treat it like it's totally different. And I had never understood why, and now I think I do. The one thing that appears to be different is this. That negative sign does not mean reflected over the y-axis like it would with a polynomial. In other words, if I told you y equal x squared, and now I said y equal negative x squared, that would be a reflection over the y-axis, making it look exactly the same as it should. You can see that both of these are y equal x squared. So a parabola, y equal x squared, is an even function because it is symmetrical over the y-axis. The sine function is not symmetrical over the y-axis. It's symmetrical over the origin. There's three types of symmetry. There's symmetry over the x-axis, there's symmetry over the y-axis, and then there's symmetry over the origin. And what the origin symmetry basically means is if you flipped it over the x and flipped it over the y, you'd get what symmetry over the origin looks like. Okay. Well, that's a good question. Let's just look at that. That's your classic parabola. Again, if I gave you this, that negative sign is out front, meaning it's just going to be a flip over the x-axis, right? But if I put the negative sign inside the function like this, then that's supposed to be a horizontal reflection, which it is. In other words, if I reflect that horizontally over the y-axis, I get exactly the same thing I started with, which that is x squared minus x quantity squared is the same as x squared. So with this polynomial, that x inside the function is a reflection over the y-axis, whereas with sine, it is not. That is not a reflection over the y-axis. So this is the only place where I can see that the whole transformations kind of falls apart. And I don't know why, but it does explain to me why they treat it differently. At least one out of the 6 things is different. And they call them completely different names. In other words, if I gave you this, well, the first thing you got to do is all your reflections, right? What reflection is that? Over which axis? That first negative sign. Okay. What is 2? What's that called? Okay. What is this 3 right there? Perfect. And what is that? Okay. So all of the terminology that applies to polynomials like this is the quadratic, is not that different than your sinusoid function. It's just that the sinusoid function is labeled like this. Well, D is clearly the vertical shift, correct? C is the horizontal shift. A is the vertical stretch. And B is the horizontal stretch or shrink. So it really appears to be exactly the same as the transformations of a polynomial. It's just this they call the amplitude. And this, they have an equation that relates the period. You can always figure out what the period is. It's 2 pi over b. So in one of those problems, b was 2, which made the period pi. That tells us how long to stretch out the curve. This, which we call a horizontal shift, is called a phase shift. And this is called a vertical shift. But other than that, I've never understood why they change all the terminology. They've just spent 2 years teaching people all about transformations, and the sinusoid function is merely a bunch of transformations. The only thing that's different is if you had the sine of negative x. In other words, if I made a1, b1, c0, and d0, and I said to you, well, what is the sine of negative x? You would say, well, that negative sign's inside the function, therefore it must be a horizontal reflection over the y-axis, and it is not. There are some co-properties. Let's talk about these, because these are important to remember. First of all, your trig functions are odd or even. Sine and tangent are both odd. Cosine and its reciprocals are even. In other words, if sine is odd, then cosecant is odd also. If tangent is odd, cotangent is odd. Okay? And what this means is that the sine of minus x equals minus the sine of x. And the tangent of minus x equals minus the tangent of x. This property actually helps with a lot of trig problems. And I'll give you an example here in a second. But the cosine, because it's an even function, that's just equal to the cosine of x. Okay? Now, how can this be useful? Well, if I said, what's the sine of minus 30 degrees? You could go through the process of turning that into a 330 degree angle, right? And then go through the process of translating it to a first quadrant and then figuring out what its plus or minus sign is. And it would be about a 4-step process. But if you use the odd property of sine, then the sine of minus 30 degrees is equal to negative the sine of 30 degrees, and you know what the sine of 30 degrees is, 1/2. So it's a 2-step process if you use the odd property of sines. Same thing with cosine. If I say, what's the cosine of minus 60? Well, I could go through all the difficult things to translate that to an angle in the first quadrant, or rather in the unit circle, but I don't need to. I know that that's the same as the cosine of 60, and that's 1/2. And it's in the fourth quadrant, where cosine is supposed to be positive. So all of this makes sense. The only thing that's a little surprising to me is the fact that this odd property ruins the reflectivity over the y-axis. And I still haven't quite figured that out yet, how that is the case. And maybe trig functions just behave a little differently than polynomials, but today is the first day that I realized that it is not symmetrical over the y-axis, it's symmetrical over the origin, which means you flip it over the y and the x. But these properties are very important. Odd, odd. And a good way to remember odd, even functions is really with this one. Because you can tell that that is symmetrical about the y-axis, right? That makes it even. And its exponent is even. if I want an odd function, I will look at y equals x cubed. Odd number. That happens to be an odd function also. Notice that this is symmetrical with this about the origin. In other words, if I were to flip this over the y-axis and flip it again over the x-axis, I would get what's to the left of the y-axis there. So this is an odd function, and it matches that exponent. So if you ever forget whether sine is odd or even or cosine is odd or even, use this to tell you, you know what x squared looks like, you know what x cubed looks like, you can figure out which one of them is symmetrical about the y-axis and which one of them is symmetrical about the x or the origin. All right. We got 10 to 15 minutes to go here. What else do you want to talk about? In other words, I'm not quite sure. What I've generally been doing today is giving you the lecture on the sinusoid function. We haven't, it's not a typical tutoring session for me. Usually you give me problems and we work through them both. So that's what I would prefer. In other words, these problems about the sinusoid function are one of two types. Okay, they're either going to give you a function and say graph it, or they're going to give you a graph and say find the equation of that. So it's one of those two, and they're going to expect you to be able to go both ways. Now, we can certainly online do these kind of problems. In other words, we can talk about a function and we can talk about how to graph it. And I would graph this just exactly the way I've been graphing the others. I would start with sine x, and then I would apply the 2, and then I would apply the 3, and then I would apply the 4. Whatever I come up with, that's the final graph. When they give you a graph and they want you to come up with the equation of that, you need to take a picture of those and send them to me. Because the one thing that's extremely difficult to do is to verbalize a graph. In other words, it's not that difficult to do. I just drew that graph there, and the key points that I labeled were the maximum was at 2, the minimum was at -2, and the period is 4 pi. Believe it or not, we can come up with the function of that graph from that information. Let's try. So, if I start with the general function, and incidentally, this is called sinusoid curve, but it doesn't have to be sine. It can be cosine. Even if it's cosine, it's still called a sinusoid function. Not if it's tangent, but if it's sine or cosine, it's called a sinusoid function. Okay, so let's see, this graph that I drew, can we figure out what A is? Okay, can we figure out what B is? Yeah, because B, here, let me, just in case you're not that familiar with it, B is 2 pi over the period. The period is 4 pi, so B is 1/2. What's C? 0. There is no phase shift. And what is D? There's no vertical shift. So what's our function? Y equals Correct, like that. And incidentally, that is the exact same thing as this. This tends to throw people when you put it like that. See why it's the same? Okay. So, given the graph, it was easy enough to figure out that the period was different than our normal graph. It was 4 pi instead of 2 pi, so that's going to affect B. And the amplitude is not going from -1 to 1. It's going from -2 to 2. That's going to affect A. There was nothing else going on, so it was easy enough to graph it. I could have made it harder by doing something like this. And now we got, well, that's the negative sine curve for starters. Because in other words, if I looked at a negative sine curve, typically, the thing that spots it is that you start at 0 and you go down, instead of starting at 0 and going up. Okay? So when you see a curve that starts and goes down, think negative sine curve. Also, the period only went to 3 pi, so that's going to change B. There's no phase shift, but there is a vertical shift. And that point right there looks to be at 2. So that equation would be y equals, I didn't label this, but let's label that 4 and let's label that 0. So amplitude would still be 2. It'd be a negative sine curve, so negative 2. Sine, and now what is B? Yeah, the period is 3 pi, so it's 2/3. Still no phase shift, but a vertical shift up of 2. So given the blue curve, that's the equation of it. It's basically that simple. In other words, you just kind of have to think of each of these transformations one at a time, I think. Yes, that's what you meant. Yes. Not really ambiguity, though, because the general rule is that you use whichever function has the smallest phase shift. So I could use cosine, but then I'd have to introduce a phase shift, and right offhand I don't know if it's the negative sign is going to be there or not, but x minus pi over 2, sine and cosine are phase shifted by pi over 2. In other words, if you take the sine curve and move it to the right by pi over 2, you got the cosine. Or, excuse me, if you take the sine curve and move it to the left by pi over 2, you got the cosine curve. So, you're right in that there are an infinite number of sinusoid functions that will represent a given curve. But I would never use this one because that has a phase shift of pi over 2. Actually, I think it's plus. And this one had no phase shift. So that's, I'm not sure I've ever heard a math teacher state that, but it's true. In other words, if I use a sine curve and I get a phase shift of pi over 4, and I can use a cosine curve and I get a phase shift of 3 pi over 4, I'm going to use the sine curve. Always going to use whichever one has the least amount of phase shift. Doesn't really matter the direction, it's the amount. Okay. Yeah, I suppose that'd be a good way of putting it. Yeah. I don't think you would get marked wrong if you use the cosine curve. In other words, it really is true that y equals sine x that is the same as cosine of x plus 1 or pi over 2. Notice what happens if I graph the sine curve. This would mean I would move it pi over 2 to the left, correct? So this point right here would start right there. And what I would end up with is the cosine curve. That's pi over 2, exactly. In other words, all I did was I took this curve right there, and I moved it that way, pi over 2. And what I got was the red curve, which is a perfect cosine curve. I might have this wrong here. In other words, I'm not sure this is right. I know what I meant. I meant to take the cosine curve and shift it left, pi over 2. Actually, the equation is the sine curve shifted left equals the cosine curve. So I do have it backwards. The red is the correct expression. And go ahead. And these are called cofunctions. Let's talk about that because that's another important thing. By definition, sine of x equals cosine of 90 degrees minus x. All cofunctions have this property, including the vice versa. Okay? So, same with tangent. These are cofunction properties. You still there, Garrison? My phone just double beeped. I think I lost the connection. You still there? Garrison? Oh, okay. I thought I'd lost the connection. Cotangent x equals tangent of pi over 2 minus x. So all of these cofunctions are shifted by 90 degrees. And that's why the sine of 30 degrees is the same as the cosine of 60 degrees. But these cofunction properties are going to come up on any trig test too. And it also shows you that how the cosine is shifted relative to the sine graphically. Even though this is a little different than x minus c, you get the idea. Okay. Garrison, you got any other questions for today? Okay, I'm going to let you go. Try to have some problems, if you could, for our next session. Certain trig topics I can lecture for an hour, like the unit circle or the sinusoid function. But in general, for me to really help you, I need to know what you're dealing with in your class. All right, I'll talk to you next time. Bye-bye.